square in the bottom, right? So I think this is an actual thing.
Yes, I saw it live.
Oh god, it's
Live
happening.
already.
Oh god, it's happening. Oh no.
Oh, but the thing is, this will lag a bit, no?
Probably?
I guess. So if you want to listen to Discord, then don't listen to Twitch. If you want to listen, please then don't listen to Discord.
Yeah.
Now I'm muting my Discord.
Explanation on screen.
What?
Will you be doing like any on-screen explanations?
Almost certainly, yes. I'm going to be looking at the slides, the textbook. I'll be probably drawing some things.
I guess you might want to share screen here as well then.
Oh, right. Yes, that's what I wanted to do as well. Apologies.
Wait, share screen.
This will be here, and then
Is
this
it
will
me
be...
or is there 34 viewers in Twitch?
There's no freaking way there are 34 viewers. That is absolute BS.
I saw the 34 there. I don't know.
Watch now with 34 viewers? What the heck?
Let's go.
I'm borderline losing it. What the hell is going on?
All viewers, 34 viewers, please follow him so
Unlock the achievement.
Yes. Following is free, guys. It's not subscribing.
Oh, hey, you can just get all of us to just vote for you for SMC, you know.
But SMC need to do things. I don't want to do.
I mean,
I used to do those kinds of things in secondary school, but those things are not the best thing. Not for me, I guess. Also, the only reason why I have a speedrun timer is because that one of the tags is speedrun, so I can put this timer and say it's a speedrun. See, I can time it. And then I can pause, then I can reset. Wow, look at that! I guess... Whoa, a lot more humans have appeared. And it's almost 10 o'clock. I am low-key scared. Exactly, where I got time for SMC? Go Home Club is eternal. Oh, thanks, I appreciate it.
Hey, we need stickers.
Oh, what? Okay, wait. 30 seconds till the run begins.
We need pop stickers.
I won't actually be speed running because this is to teach, so I won't be going that fast. Oh, if I'm going too fast and the terms I'm not saying are not making sense, feel free to stop me right then and there so I can tell you in more clarity. Yeah.
Is anyone recording this?
9, 8, 7, 6, 5, 4, 3, 2, 1, go! Alright. Linear Algebra, Finals. Chapter 1 is pretty basic. I trust that Chapter 1 should be perfectly fine for everyone. Maybe the only hardest part is this over here. Coordinate conversion with matrices, coordinate conversion in general. But I trust that these three are okay. So I'm quickly gonna run through points and stuff. This should be here. That is not the right place. Okay. And I should have set this up. I'm losing time in my speedrun. Holy shit. Okay, anyway. Points are points. What is a point? A point is just if you have a space just lying around. Maybe you have your E1 axis and you have your E2 axis over here. A point is just a place with coordinates. You can have point P, usually there's a line above it, and it will have certain coordinates. Maybe this could be like, that's like 2 on the E1 and maybe 2 on the E2. But you get the gist. Points have coordinates and they exist in a space. Now, as for global systems, we will always use E1, E2, E3 forever and always. Yeah, there's always E1, E2, E3. E1 is of course 1, 0, 0. I think it's more likely that they'll do 3D stuff in finals. So for the most part, I'll be using 3 dimensions, except for these 2D interactions, because these will be more of a recap. Then we will get to 3D later on. So E1 is 1, 0, 0. E2 will be 0, 1, 0. And E3 will be 0, 0, 1. Forever and always. These values do not change no matter what. Now, that is the global system covered. Now we head on to the local system. What is a local system? A local system is a system that is defined by its own 2 vectors and a origin point, so to speak. So for the global system, your origin point is 0, 0. Now, for a local system, it can be hiding somewhere inside. No, that's not the right way to say it. It is... A local system is a system that is different from global. What do I mean by this? It will have its own axis vectors. I put A1, A2, A3 here, but since I'm drawing on a plane, I can only do 2 dimensions, so we'll stick with that. Let me just delete this. So we can have our system maybe down here. Let's say we have our origin here, we have A0, a point. Then we can have our A1 vector. And maybe even our A2 vector. It doesn't even have to be perpendicular, you never know. This is a local system. And if this was like a 1x1 box, like a standard 1x1 box, and this is the point at the end, the standard 1x1 box in this coordinate system will look a little something like this. It depends on the axis vectors and where they are. And yeah, you can express points in the global system as points in the local system. What is that? That is coordinate conversion. If this is 1, 1 in global, if you don't put anything down here, if there's no G or whatever, no A or whatever, that is global by default, forever and always. And then we can do some sigmath, and we will eventually find out what this point is in relation to the A system. So it's the same point, but we are just converting its coordinates to something in the A system. Once you have an A down there, that means it's for that specific system. Oh wait, what is this? Oh, it is all going to be 3D in finals. Oh, okay. Thanks for that. I should check chat more. What the heck? Wait, hold on. Why are there emotes in the chat? Hold up. Wait. Where's the... Oh god. So many windows. What's going on with y'all? Okay, sure. Whatever. Alright. Coordinate conversion. So let's use an... shall we do an example? Okay, let me get some numbers. Where's the lab? Okay, let's delete all this. That is the wrong tool. Delete all this. And let's say we have our original system. We have E1. Oh, that was a lot of lag there. E2. Maybe I should not watch my own stream. Yes? What? I hear something, but I can't tell what that is. Where is the thing? Okay, sorry for being so disorganized. This is very hastily put together. So let's say we have our E1, E2 and E1 coordinates, and we have a point, say, at 1, 1. This is 1, 1 in global. And we have a point maybe further down that is 3, 1 in global. Now, if the origin is there a nice origin I can use? Come on. Alright. If the origin is somewhere down here for this new system, it has its own A1 and it has its own A2. Also, for a local system, the A1, the length of A1 and the length of A2 may not be the same. So keep that in mind. And we have A0. So we have something from global, and we want to convert it to local. So this will be, where are my calculations? Okay, just a show of hands. I'll just say out if you need it. Do you guys really need me to go through this one? Because it's fairly basic, and this chapter 1 stuff, there's not really that much of a chance to be tested. It's more everything else that's a big deal. So what do you all think? Should I continue with chapter 1 or just skip to chapter 2 instead? Because I don't want to spend too much time doing something that is too basic.
Possibly conversion with matrices, I guess.
Conversion matrices, okay. Yeah, alright, I'll go to that now. This will be, okay. So conversion with matrices. Let's say we are going from a local system, a point in the local system, and we want to find its global coordinates. So we will say that if a point is at 1, 1, no. 1, 1 in the local system. If you have a point in the local system 1, 1, and you want to convert it to a global system, this will be the origin of that system. In this case, it's A0. Why is my paint lagging? Holy shit. A0 plus A1. Then we take the first coordinate, which is 1. 1. And plus the second coordinate, A2. Notice that they're both 1 here, so it doesn't look very obvious. But it is the coordinate in the top is the number of times you have to multiply A1. The one at the bottom is the number of times you have to multiply A2. And when you eventually calculate this out, you will get an answer in global coordinates. Now, for a linear transformation, let's say this point was let's say the local system is a linear transformation. So instead of the origin being somewhere different, it is, let's say if this was our normal grid, we have E2 and you have E1. Let's say the local system was maybe like this, A2 and A1. Here you would have the vectors for A1 and the vectors for A2. And let's say you wanted to convert something from the A system to global. You can form a matrix, the matrix A, using the A1 and A2 vectors. A1 and A2. Let's just give this as 1, 1. This is positive 1, y is negative 1. Dude, Paint, why are you lagging? Come on. And then, note how I put these vectors side by side? Just put in the numbers, and they'll be side by side just like that. So A1 first, you put in A1, which is 1, negative 1. Then A2, which is 1, 1. This is the matrix that defines this system, this local system of A1 and A2. Now, to convert coordinates, what you would do is to get a point in global. Let's say you do point like this. It would be the matrix times that point with A coordinates. So it would be 1 minus 1, 1, 1. Then followed by whatever local coordinates you have. So what happens with this is that once you do this multiplication, you end up getting a point with global coordinates. So this is a fairly important part. When you do coordinate conversion, later on we'll get to morphing and transformation. That's the opposite. You have to multiply by A inverse to do a similar thing. When you do with A, let me just erase everything. So with look, I need to make sure I not mess this up. With this goes from local to global, and this is coordinate conversion. It's very important to know that this is coordinate conversion, and the and that morphing are two separate things. Now, to do the opposite, because we've discovered matrices already, we can find that any point in the local system is just the inverse. We'll get to that later. Just note this for now. The inverse times. Hello, Paint. Come on. Times that global point. So when going from global and trying to find a local, and this is coordinate conversion, you do the inverse. This is just the normal matrix. So please be wary of this. This was tested in like quiz 3, I think. Quiz 3 and midterms, if I remember. Yes. Okay, so that's chapter 1 basically. That took 14 minutes. That's okay, I guess. Now, chapter 2, vectors. Vectors, I'm sure you know, if you have a point and another point, let's say it's P and you have Q. If you perform a subtraction, Q minus P, you will get a vector pointing in this direction. If we call that vector V, we can say that V is equal to the point Q minus the point P. That's what a vector is. Now, vectors have a length and they have a direction, but they do not have a location. What I mean by this is that the fact that vector V may look like it's coming straight out of P and going straight to Q, but I can also move this vector if I wanted to over here, same length, same direction, and it's just as valid of a V as that other one is. As long as it's the same length and direction, it is the same vector. You can move vectors around. You can't do that with points. Points need to stay where they are, but vectors can be moved around freely. In the textbook, I believe they say that vectors are in real space or something. Something like this. Okay, never mind. You just have to know that points have fixed locations, vectors can move around. Yep. Right. Barycentric combinations. Now for this, let's say we have 2 points again. And once again it is P and Q. Now we already know that Q minus P creates a vector, but you can also form points with this. Now, the important thing to know about points is that as far as the mathematics are concerned, the only truly valid operation is point minus point. That's okay. If you do point plus point, that's invalid, and if you scale a point, say 3 times a point, that is also invalid. Now, this being said, we're about to see something that looks contradictory to this, but I'm afraid you just have to hang with it. So, let's say I draw a line from here. This line is known as the convex, what's it called? Convex region. What does that mean? It means that when we have our barycentric equation, let's say we have some point, let's say point X, and is in between P and Q, point X will be some part of P and some part of Q. This is what is known as a barycentric combination because the coefficients sum up to 1. Oh my god, Microsoft Paint! They sum up to 1. And a convex region is when the T here goes from 0 to 1. So anything that is out on this side... Sorry?
Oh, sorry.
Oh. Yeah, so anything that is out on this side or out on this side is not part of the convex region. Only the part in between the points, this part right here, that's the convex region. So if that term comes out, now you know what it means. Okay. Next is linearly dependent and independent vectors. What does that mean? It's a very routine way of saying whether things are parallel or not. So if you have a vector going in this direction, and you have another vector going in the same direction, could be longer, could be shorter, doesn't quite matter. But if they are parallel, they are said to be linearly dependent. Horrible handwriting. Another way to say it more mathematically is that one vector can be expressed as the scalar multiple of the other. What does that mean? It means that if this was, let's say, 1, 1, and this was 3, 3, we can see that, hey, 1, 1, oh, come on, 1, 1 is 1/3 of 3, 3. We said that V was a scalar multiple, let's say k, some number, of the other vector. Once this comes about, you know that these vectors are parallel, which means these vectors are linearly dependent. If you can find a scalar multiple like this. On the other hand, if you can't find a scalar that makes this true, that means they are linearly independent. Doesn't mean they're perpendicular, it just means that they're going in different ways. See, like these two. This V and W are independent because they are not parallel, and you can't find a scalar multiple. Okay, next is the dot product, our all famous star bang bang. The dot product formula, you all should know this by now, but in the very weird case that you don't, here's the dot product formula. It is magnitude of V, magnitude of W, times cosine theta. This is the geometric formula. I'll draw a triangle later so I can show it to you. And then the computational one, like how to actually get like the numbers. If you don't have these numbers, you can do the other one, where it's V1 W1 plus V2 W2 plus V3 W3. This is for the maths, and this is for the computation. Wait, no. That's for the geometric things. Geometric. Now, for this geometric part, let me go draw a triangle. This should be fine. We have V, and we have, say, W. Oh, W at the end. Now, this sign, I should use a different color. This part here, with the two lines, that represents magnitude. So if you see this, this means that that is the magnitude of the vector, or the length, how long it is. And this cosine theta, this theta represents this angle between the two vectors, like so. Oh, come on. And the dot product, hold on, how do I say this properly? Cosine theta. Oh, keck, I screwed it up. Alright, that shouldn't be there. Because our star bang bang, the dot product is also known as the length of projection onto a unit vector. A unit vector is a vector with length 1, so let me just draw W really small. Now, the length of projection of V onto W will be this length. Now, using basic trigonometry, we can see that, okay, we have a right angle triangle, we have our theta, and we have the magnitude of V on one side. And we want to get this side. So using basic trigo, we can understand that to get it, it will be, that part will be equal to magnitude of V cosine theta. Oh, come on. Yeah. But note that this is only when W has a length of 1. If W is bigger, we need to scale it by how big W actually is. So that's why there's a magnitude of W there as well. That's how you get the full dot product formula. So most importantly, just remember this one. This is how the thing is geometrically seen. And this is how you get the actual number from the dot product. Okay, dot product done. Dot product, the values of the dot product can range from negative to positive. But in particular, when the dot product is 0, it means that two vectors are perpendicular. This is a very useful property to know. And it's something you should always keep in the back of your mind. When they say two vectors are perpendicular, you can maybe write this down somewhere and say, okay, it's property I might have to use later on. Okay. And projection of vectors. Okay, let me just do that. Right, so we have our vectors. We've got our usual suspects v and w. And the projection is, I kind of mentioned it just now, but the projection of v onto w is this part here. Sometimes it's written as projection of v onto w. You can think of the smaller one being like the base that you project onto. Now that's how I see it personally. So this is one part of the vector. You can also try to find this part of the vector, because you know there's like a horizontal part and a vertical part. So now I want to find the quote-unquote horizontal part. Now we have this projection of v, and we will have the vector v itself. So if we have this vector and we have this vector, well, what we want to find is this one. We want to start from this point here and end here. And one way to do that is to swap this vector around. So if we turn it around, we can see that it'll be something like, oh, that's way too small actually, holy shit. Like this. Which means that in the textbook it's written as u perpendicular, if I'm not wrong, which is also fine. U being what the projection is. That will be equal to the original vector you're trying to project, in our case v, minus the projection that you had just now at the bottom, this red part here, which is v minus the projection of w onto v. Now, I have not gone through the actual projection formula yet, so I'm going to do that now. The projection vector is, why is paint lagging? Come on. It is v dot w over the magnitude of, we're projecting onto w, so magnitude of w squared times w. This is the projection formula. It is very important you remember this. This is to get the projection vector. If you wanted just the length of projection, which I'm going to write as this, of w onto v, this length will be v dot w over magnitude of w. This is the length of the projection vector, and this is the vector itself. Very clear distinction. Do not mix these two up. Yeah. I guess that's it for chapter 2. So now we move on to chapter 3. Lines. So there are how many different forms? Like three or four different forms? The first type of line is a parametric line.
If I'm not wrong, there's three kinds of lines, I guess.
3 lines, yeah. I can like half count barycentric, but it's like kinda there, kinda not there. A parametric line will be given as, that's not a good looking L. L bracket t is the parameter that you're changing, will be equal to a given point plus that changing t multiplied to a vector. So how you can see it is there's a point here. Maybe there's a vector going this way. This is our point P. Point P. And let's say we do t is 1. So it will be from here plus 1 times of v. You end up here. You get a new point. Plus 2 times of v. Add another v. You get another point. So by changing the t, you get more and more points in a straight line. That's how you get a full line from this equation. That is one form. You can also see this as a barycentric equation. This isn't really like another alternate form, it's just another way they can write parametric. Where they have, it looks exactly the same as the barycentric form that I showed you earlier. 1 minus t p plus t q. After that is the implicit form. But I think since we're working with 3D in the finals, I'm going to skip it. You can just know it exists. Yeah, just know it exists. Other than that, we have. No, that's also implicit, so not really. Okay. These are the only two forms that lines can have in 3D. In 2D there are more, but since we're not doing that in finals, it's okay. We'll just stick to 3D. Line types. Conversions between line types, there's only really one line, so we can't really convert per se. Alright, let's do this one. These things are important. Distance from a line to point. Let me clear everything again. Okay, we have our line, we have our P, and we have our V. And you want the distance from a line to an external point. So let's say it's a point around maybe here. This is point Q. We want to find the distance from this point Q to the line L, where L is P plus T V. Now you could get this distance, or this distance, or this distance, or this distance. You can see there are lots of different distances to get. So because there's so many, when they say distance from a point to a line, they mean the shortest distance. And the shortest distance will always be at a right angle. Now, how do we get this? Distance? We have a point and we have another point. So we can do point minus point, we can get a vector. This one. So we can get the Q minus P vector, and we... Okay, how do I want to say this? Alright. And it'll be very useful if we could find this component of this vector, because that's exactly what we need. We need this length. This is the length that we need. So you want to project it to something that is parallel to this line. You want something parallel to this line. So what we do is, we have our V. With our V, we can get a vector that is perpendicular to it. So if V was V1, V2, a vector that is perpendicular to this would be minus V2, V1. Alternatively, it can also be V2 minus V1. Whichever one of this doesn't matter, as long as you choose one, it'll be fine. If you do that, you will get a vector like this. Same length and everything, just perpendicular. Let me write V perpendicular. Now you see that we have Q minus P and we have V. So all we have to do is find the length of projection of Q minus P onto this perpendicular V that we found. So this would be the length of the projection onto V perpendicular Q minus P, put that in brackets, which will be Q minus P dot with V perpendicular over magnitude of V perpendicular. All this is given information. Sorry, Q and P are given information. V perpendicular is something we found out ourselves using this. Yeah. Now that is distance from point to line. Now we have the foot of a point on a line. Now for this one, it is a similar thing. Wait, is it? Yeah, okay. Let's use the same diagram. I'm going to erase everything else. Now, the foot of a point is having a point, let's say Q again. A foot of a point is a point that is the shortest distance from that point to the line. So because the shortest distance is this, is this one right here, the foot of point Q will be here. Call it point R. Now R can be found out by doing the following. You have Q and P, so let's make a vector. We've got Q minus P again. Now we have a point P and we have a point R. What we would like to do is to get like a vector that goes in that direction. And would you look at that? If you have Q minus P and you project it onto V, that's pretty much exactly what we want. We get this red bit over here. Then all you have to do is P plus the red bit equals R. So let's do that. R, hold on. Okay. Well, I'm like losing focus. We want the vector itself, so we do this, and we're projecting onto V, magnitude of V squared. Note that magnitude of V squared can also be written as V dot V. They mean the exact same thing, they give the exact same number. So you might see this in like certain questions being like, oh, determine if this is like the projection vector or something. So you know what to look out for. One thing that it might give you, whether it's this form or this form. And this times V. This whole bit is this vector here. Yeah. And now that we have that vector, we can add it to P, no problem, to get R. So R will be P plus this vector. Now P is given, Q is given, P is given, V is given. All of this is given information. All you have to do is fill in the blanks. And you should get a nice point after that. Now, intersections of lines. Here we have, okay, two lines. Let's say we have line 1, which is P, L, T is P1 plus TV1, and we have L2, which is uses the parameter S, P2 plus SV2. Two different lines, and we want to find out where they intersect. So we want to find a point. Like we want to what are the words? It'll be, okay, this is L2, this is L1, this is P, and this P1, this is P, P2. Now we want to find this intersection point here. What we want to do is find like a general form for each point and then equate the two together. So we know that for any point on L1, any point on L1 will take the form of P1 plus some T, we don't know what it is yet, but just roll with it. It'll be some T and V1. Now, since this point is a point on L1, and we want it to be the intersection point, this point must also lie on L2. Sorry, 1 second. Okay, alright. Okay, so we have this TV1. That means that, oh wait, no, I'm dumb, never mind. Okay, we have this general form. This is for a point on L1. This is still true, but we're not going to use this property right now. And then we have our point, whatever point, on the second line. Now, whether in 2D or 3D, you'll still be able to use these steps. So I'm just going to write it in 2D because it's simpler. It'll be P1, P2, plus S, V2, V1. I'm sure you can all agree on this, which is, let's say we combine them, we get P1 plus S, S, V1, P2 plus S, V2. Now, this can be compared with the one from L1. So it'll be, oh my god, they're named the same. Okay, it's P1X. Okay, now I'm making it more complicated. I apologize. But basically what you have to do is, you will add these up. This will be T, and you'll get something like the points X and the points Y plus, you get T in this case. It will be the vectors X and the vectors Y coordinate. What you can do is compare these equations. So since an intersection point lies on both lines, these two must give the exact same numbers. This means you can write a set of simultaneous equations where this is one set and this is the other set. This is equation 2. So you solve for simultaneous and you are done. You're almost done. Once you find T and S, you sub T and S back inside here, and then you can get your intersection point. So far, so good. Am I making sense? Am I like too cluttered or
Yes.
anything? All right. Okay, that's chapter 3 done. Now we have 4 and 5. Okay. Now, this is where the matrix gets introduced. A matrix is a set of numbers enclosed in square braces. They can be 2 by 2, or they can be 3 by 3. We're definitely going to see the 3 by 3 one more often because, you know, everything's in 3D now. Now, these matrices, you can think of them as representing a transformation, where later on we're going to talk about E1 prime and E2 prime. This is your E1 prime. This is your E2 prime. Similarly, this is E1 prime. This is your E2 prime. Whoa. E2 prime, and this is the E3 prime. And by these little squares I'm drawing on the bottom, I'm meaning the whole column of that thing. That whole column is E3 prime. And multiplication. Okay, for properties of a matrix, it'll be like I think I should look at the slides. I don't want to say anything wrong here. Let me just lecture 4 points matrices. Okay, the properties of the matrix are later, so I guess we'll do that later then. Now with matrices, I've said that these represent like transformations, and this is true for all like the square matrices, the 2 by 2 and the 3 by 3. Now what this does is morph points from one place to another place. After morphing, the coordinates will still be the same, but they'll be physically in a different place. What do I mean by this is that if you have a system with our usual E1 and our E2, let's do a simple scaling matrix. And this is our point, which is 1, 1. And we do a scaling. The arrow is too big. We scale. Let's say we scale the E2 axis. So it'll be maybe like this. You have E1 still the same, but E2 is all the way up here. E2 prime, sorry, E1 prime. Our 1, 1 is now a lot further from the E1 axis than it originally was. But it is still 1, 1 in this new system. This is what I mean by the coordinates stay the same, but the coordinate that they are physically in a different place. Was there a question just now? No? Okay. Now, that is what a matrix can do. That's a transformation. Remember that this is different from coordinate conversion. Coordinate conversion, you're just getting another name for this point in another system. Morphing, you are physically moving the point to a different place in space. Now next is the general plan, which is fairly simple, but it's also very powerful. For these questions, they'll be like, okay, get the matrix that describes the following transformation. So they say, oh, it performs let's say a projection onto the line that is parallel to this vector, for example. And it says get the matrix. This is like the standard question where you're given some input information and said, okay, get the matrix. How do we do that? We do that by finding what E1, E2, and E3 in this case will become after what will they become after the transformation? So the way to do that is to find a formula that works for any general vector that is being transformed. So let's say for projection, it will be the projection formula. Projection onto, I should not have put V. Oh wait, no. For any vector W, I like using W as my unknown, project onto V and get W. Here we have a formula that takes in W as an input and gives you what W is after the transformation has happened. So using this formula here, we can sub in E1, we can sub in E2, we can sub in, oops, that's not meant to be there, E1, E1, E2, E3, and then out the other end, we'll get E1 prime, E2 prime, and E3 prime. Once we get these three matrices, then we can build our matrix A, which is E1 prime, E2 prime, and E3 prime. And then since you found like each E1, E2, E3 prime will be like its own like vector with like three things in it, 1, 2, 3. It'll be a 3 by 3 matrix. So it's something here, 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 something here. 3 by 3. So to reiterate, find the general formula, sub in E1, E2, E3, and make the matrix. These steps are super important. Now we go on to scaling. These are just different types of linear transformations. Linear transformations meaning they work on vectors. Linear means vector, affine means point. Now for scaling is fairly simple. If that's what we did just now, if you have I think for this I'll use John's slides. That'd be much better. Can I do this? Yes, okay. Here we have a scaling matrix. Did he write the thing out? No, okay. So a scaling matrix, you just have to see which axis it is getting scaled by. Scaling is always parallel to E1 and E2. So there's no need to worry there. You just have to multiply the how much they scale in that direction. So it says, this example question says, find the matrix that scales by C1 in the x direction and C2 in the x2 direction. X2 is y, x1 is x, for example. This means that if C1 is being scaled by C1 in the x direction, 1, 0, which is, let's say here, If it's getting scaled by C1, let's say C1 is 3, this is E1, this will be E1 prime. The length is 3 times as long. So, what you have to do for a scaling matrix is just multiply that number in. So if E1 was 1, 0, E1 prime is 3 times 1, 0, which is 3, 0. Same thing with E2. For projection, we just use the projection formula. There's not really that much to say. No, there is something to say. Okay. The projection formula will be something like this, where we have our axes. You have some vector, some line that you're projecting onto, basically. Sorry, some vector you're projecting onto. I just draw a line to make it easier for myself. You have some input vector W, and when projected onto V, it becomes like flat, basically. W prime. So, step 1 was to find a general formula for the transformation. Here it's just a simple projection, so we can say safely that W prime is equal to the projection of W onto V. And if V is a unit vector, you can simplify this even further. If V is a unit vector, this would just be W dot V times V if magnitude of V is 1. Sometimes it is, sometimes it isn't. That's why, me personally, I like to leave it in the general case so that I leave my options open. Once you have this, you can now sub in E1 and E2 and E3 to get E1 prime, E2 prime, and E3 prime. Then step 3 is to build the matrix. These steps will get very repetitive. Only the first step really changes. Steps 2 and 3 stay the same all the time. So that's for projection. For reflection, this will be okay. So far, any doubts, any queries? I am going to take that as a no, so I will continue on. Now we have the reflection. I'm gonna skip basic. Let's just use general instead. Because for basic, it is just like if you have E1 here and E2 here, and you like reflect along E1, you just get E1 prime, which stays the same, and E2 prime, which points downwards. So E1 prime mostly the same, which is like 1, 0. And it'll point downwards for E2, so it'll be like 0, minus 1. 0, minus 1. And then the matrix would be 1, 0, 0, minus 1. That's for the basic one. For the general one, which is probably going to be far more useful, let's say we have our line of reflection determined by the vector V. Okay. We have V. We have our axis, and we have some vector, maybe say W. Come on. Now, when W is reflected across V, it should look something like this. W prime. This diagram looks terrible, so I'm going to draw it in a separate way, which will be here. we have W on top. We have W, what? No, W on top. W prime at the bottom. And vector V is going in this way. And this is like the reflection line. There are two ways of going about getting W prime, both of which are equally valid. But I'll just go through the way that I use, I guess. So for this, we know that the horizontal part of the W's is the same. They both go to the left in the same amount. What makes them different is that one goes up and one goes down. So we can say that W prime is the part that goes left and the part that goes down. But since the original W is going up, we want the negative of that because we want to go down. Because we want to go left and down. So the up. Now this portion is the, hold up. Yeah, this portion is right here, which is the projection of W onto V, which is okay because we've been projecting a lot of stuff and it's just a projection, so it's fine. Projection of W onto V. Now, we want to find the up part. Oh, come on. Alright, the up part. Now, I mentioned earlier that there is a perpendicular part to the projection. Like if you have a projection, let's say U was a projection, U perpendicular would be this part. It goes perpendicular to the projection. And how do we get that? I said earlier that it is the original vector minus the projection. This projection is the same as this, the exact same term. Now if we simplify this, we will get, I do not have space, I'm just going to write it here. Let me just make sure I'm correct. Yeah, okay. It will be 2 times the projection of of W onto V minus W. This is the general form for any reflection thing. So if you put in your W vector, your input vector, you get W prime as your output. So that is the general reflection matrix. Rotation, I'm fairly certain all of you guys can do rotation except with respect to 2D. Rotation in 2D is just, whoa. Rotation in 2D is just the cosine of the angle you want to rotate by. Cosine on top, top left, cosine on bottom right. And then you put minus sign, and then sine. I can go through the geometric proof, but I think it's okay if you guys just memorize this. Now for 3D, it will be depending on which axis. In 2D, this works for any rotation you're trying to do. But in 3D, you need to consider which axis you're rotating by. So rotation, let's say it's by E1. If we are rotating by E1, the E1 axis should not change. So, since E1 does not change, E1 prime should be the same as E1. So we can write 1, 0, 0. Now for the others, do I have the slides? Should I look at the slides? It's all the way in 3D though. Where is it? Dun 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 dun. I'm surprised my computer's keeping this up. Like, it's stuttering every time I draw in Paint, which has me concerned. But it's somehow working through it. Okay, rotations in 3D. This is E3, this is E1. Okay, we're in E1 right now. So, as you can see from this diagram, you have E... Can I draw? I can. Alright. You have E2 over here. This one. Blue is not a good color for this. You have E2 here. And you have E3 here. Now, when you look at it at this view, where E1 is the axis does not change when it's being rotated about that same axis. It can be viewed as a 2D rotation, where E2 can move to E2 prime, E3 can move to E3 prime. So, because it's just like a 2D rotation, we can just put this part. Oh my god. We can put this part down here. Cosine, cosine, sine, and minus sine. This is 0, this is 0. Now that's for E1. For E3, it is a similar idea, where it is rotating by E3. Since E3 is the axis, E3 should not change. This means that E3 prime is still E3, which is 0, 0, 1. And we can put zeros down here, and it will be the cosine cosine minus sine and sine, just like 2D. All these black boxes are the same. Now, where things differ is in the when you rotate by E2. With E2 prime, initially it begins the same, where E2 is your axis. If E2 is the axis, then that vector should not change. So that means E2 prime is still E2, which is 0, 1, 0. And in this case, it will be a 0 here and a 0 here. But for E2, you must be very careful. This is still cosine. This is still cosine. But the signs swap. Positive sign is here, and negative sign is here. And of course, with all these sine and cosine, I actually have a theta there, but there's enough characters as is. Let me just make sure. Yep, minus sine and sine. So this you have to take note of. E2 is the weird one. E1 is fine, and E3 is fine. It's just E2. That's for rotation. I went off tangent to 3D, but I guess we had to get there anyway. Now we do sharing. So far, any questions? And I guess not. Okay. Alright, shearing. For a shear, in 2D, it will look like this, where if you have, let's say, E2 and E1, and you shear parallel to the E1 axis. This is our shear vector S. It's like got a length of like 2. not drawn to scale, of course, and we shear this E1, since it's on the shear axis anyway, it does not change, so E1 will just chill. E1 prime stays the same, but E2, since it's 1 unit away, this is 1 unit away, and then it'll apply the shear 1 time. The shear is 2, so it goes 2 in this direction, which means E2 prime is now here. This is where the original E2 was, and this is adding by S. Not drawn to scale, but I hope you can get the idea that this top part will stretch this way, and things below it will stretch the other way. And the further you are, the more you stretch. So the distance matters. The basic shear is just shear is a H, because S is for scaling LMAO. If you shear parallel to the E1 axis, the situation we have here, E1 will stay the same, but E2 will be like this. This S is how much you shear by. If you were to do it parallel to the E2 axis, it will be 1S01. Now, generally, we don't really shear with the axis. It's usually some random axis, so that's more important. So let's go through that. This can kind of be used in Gauss-Jordan if you do it the more geometric way, but for me, I just do it the more mathematical way. Now, general shear. So we have a system. We have our, let's say we have our vector W like here. And we have W prime, which we can put maybe here. So our shear axis is this way. And here's the thing about shear questions. When given a shear axis, you will always be given a normal as well. Because without this normal, you literally cannot do the question. So it's important that you find these S vectors and the N vectors in the in the question. So it will be okay. Then I will do this, and this will be S. Okay, so like I said before, the distance that you go from the shear axis makes you shear more and more. So the further you are, you shear more, and you shear more, and you shear more, and if you're on the other side, you shear more and more and more. So that means you need to find the distance of of W from this shear axis. Now let me draw this in a neater triangle. We have our N, then we have our, say, our S, and we have our W, both of which are in the same corner. Oh dear. Okay. Now, what we want to find is this distance. So, we project W onto N. We find the length of that projection. N is usually a unit vector in these questions, but just take note if it isn't. So once we find this distance, all we have to do is multiply it by our S. because like we said, the further you go, the more you shear. This means that for any vector, any general vector, it'll be that original plus this red bit, which is w dot n times s. This is the general shear, provided n is a unit vector. If n wasn't, this bracket part would be w dot n over magnitude of n. Yeah. Does this make sense? I keep asking that, but
Will there be scenarios where n is not a unit vector?
it's possible. I know in the labs there is one question, I think like lab 6, lab 7, maybe 6. There's one where the normal is not a unit vector. So you have to do a bit more math to get the proper matrix out in the end. Yeah. So this is the general shear. Very useful. Now, composite maps. Basically, what this means is you can mix and match stuff. You can shear, you can rotate, and then after that you can like reflect as well. But the order in which you want and the order in which you write are two different things. Delete this. So let's say we want to scale. I'm going to denote that by the matrix S. Then I want to rotate with the R, theta. And then after that, shear. Shear parallel to the E1 axis, for example. I want to do it in this specific order. Scale, then rotate, then shear. However, when you write it in your actual paper, you will write not S. Sorry, wait. Yeah, you won't write it as S, R, theta, and then H. It is the opposite. What you want to do first is on the rightmost side. So let's say you have your input vector V. In general, for any map, I should have said this earlier, oh no. In general, for any map, it is V prime. The output will be whatever transformation matrix you have times the input vector. Now we want A to comprise of all these three things. Yeah. So to do that, we want to do... the first thing we want to do is scale. So we put that right next to our input vector. We want to scale first. Then, only once that is done, then we rotate. And then, once that is done, we shear. So without the brackets, maybe I should get a tablet. No. Without the brackets, it looks like this. They are in the reverse order that you wanted them. So be very careful. You know your sequence. What you want to do first is always the closest to the input vector. That gets applied first. Then you do the next one. Then you do the next one. So be very sure of this sequence. Order multiplication, composite maps, yes, okay. And for matrix multiplication, if you had A, then B, then C, then D, this works for 3 by 3 as well, but 2 by 2, I'm doing 2 by 2 here for simplicity. E, F, G, H. How do you multiply these matrices? This would be the end result of this will still be a 2 by 2 matrix. So what I like to do is, okay, I do element by element. 2 by 2 matrix only has 4 elements, so I want to do the first one, which is the top row, left column. Now, the matrix on the left decides what row it is. The matrix on the right decides what column it is. So if I want first row, it's this and this that I'm looking for. So first row, first column, it will be A, E plus B, G. Now, then I do the next one, first row, second column, which is this one. I need a different color. This will be AF, then plus, B, and then H. I think you guys can kind of see the pattern here, where you choose what column you want to start with, sorry, what row you want to start with, and then what column you want to start with. So the one on the left does the rows, the one on the right does the columns. Yeah. Then you can fill that in, I guess. Okay, next thing, determinants. The determinant of a matrix, if you have A, B, C, D, if this is A inverse, oh not inverse, sorry. The determinant of A, which is sometimes written as this. Do they write it in the textbook? I'm not actually sure. Can't remember. Anyway, the determinant will be AD minus BC. This is like hard-coded. It's just how it is. It is AD minus BC. AD minus BC. I like to visualize this little cross thing. It helps me remember. Now, for determinants, they give a certain idea as to what a transformation matrix like A can do. If the determinant is 0, that means that that is a projection matrix. Because what the determinant does, like if you have a system, you have E2 and you have E1, you get this little square that's made out of E2 and E1. You can think of the determinant as how much this area is scaled by. So if it's a projection, everything becomes one line. And you can't have area on a line, so the area is 0. Therefore, the determinant would be 0. Whereas if you rotate, can I rotate like this? Wait. No, I can only move around. If you were to rotate this, say like that, and you still have that same square, it's the same area, the determinant of the matrix would be 1, because it's the same area. You times by 1, it's the same thing. So the determinant can kind of give you an idea of what a matrix is doing to a system. Determinant is AD minus BC. That's for 2 by 2, but we unfortunately live in the third dimension, and that's where things get annoying. So if we have A, B, C, D, E, F, H, I, oh, that took me embarrassingly long to realize. Wait, A, B, C, D, E, F, oh no, I can't alphabet. A, B, C, E, F, G, H, I, wow. The determinant for this will be to, okay, will be to 1 by 1 block out the rows and the columns, and you'll be left with the 2 by 2 matrix, and you find the determinant of that. What does that mean? Okay, let's start with the let's use the top row as reference. You can use either the top row, middle row, or bottom row. But Jan always uses the top row, and even though all the results, whichever row you pick, are the same, I just default to the top row. So with top row, let's do A. A, let's cancel out the column of A, let's cancel out the row of A. We're left with E, F, and H and I. So that is, let me write, determinant of A is, since we blocked out A, that's the one we're using as reference, so it is A times the determinant of the matrix E, F, H, I. And then we go on to the second one. Now we use B as reference. Cancel out row, cancel out column. Now you see we have D, F, G, I. So you would think that it would be a plus, and you would write things similarly, but unfortunately not. It is a minus. The reason for this, is because the signs for these things are assigned in a certain way. You start with the first one always being a plus, and you alternate from there. So it's minus, plus, here we go, minus, plus, here's minus, plus, plus. This only works, this sign assignment is only for the determinant, not really for anything else that we know of yet. And then similar process for C. Cancel out the row, cancel out the column. D, E, G, H. So it is plus C, D, E, G, H. And this can be further simplified because we haven't actually calculated this determinant. So it'll be A times E, I minus F, H. I think you can see where this is going from here. D, I, F, G, and so on and so on. This is how you get the determinant of a 3x3. Now, what is next on the list? We have an inverse. Hello. Okay. Now the inverse of again we're doing 2x2 first. The inverse of a 2x2 matrix is very simple. If you have A as A, B, C, D, the inverse is 1 over the determinant, A, D minus B, C, times, you swap A and D around, D goes here, A goes here, then you add minus signs to B and C. Minus B minus C. Then you just simplify this, and that is your inverse matrix. It is very simple. Finding the inverse of a 3x3 is stupid and hard. There is a way to do it, but there's a way to do it that's similar-ish to this, but it is not worth going through all that trouble. We can calculate the inverse of this by doing Gauss-Jordan instead, which we'll get to eventually. Now next up is a trace. This one's more of a side note. The trace and rank are more of side notes. The trace of a matrix is the sum of the elements on its diagonal. So here we have our 2x2 matrix. The trace of this matrix A is A plus D. A plus D. Did my music stop? Oh, yes. Wait, what? Okay. Wait, no. I don't want an ad. Go away. Alright. Detour. This is the trace of a matrix. I don't think you'll be told to use this very much, but you should at least know what it is. We don't have a use for it though. For a 3x3, if you had A, B, C, D, E, F, H. Oh, paint, come on. D, E, F, G, H, I. The trace for this would be just A plus E plus I. You go straight through the diagonal and you sum them up. It's a thing that can be done. Now, the rank of a matrix is the count of how many linearly independent vectors that the matrix is made out of. There's a lot of big words, so let me break it down for a bit. Let's say we have another matrix. We've got C, 2, 3, 1, 1. And another matrix, D, which is 3, 6, and then 1, 2. Now, remember that these are, we can view this matrix as two vectors. We have E1 prime, and we have E2 prime. Same thing here, E1 prime, E2 prime. Now, with this, with matrix C, you can see that no matter how I try to multiply E2 prime, I multiply by 2 or I multiply by 3, I can never get E1 prime. There is no multiple of E1 prime that gives me E2 prime. This means they are linearly independent, and since this is a 2 by 2 matrix and there are two linearly independent vectors, that means the rank is 2. And it is also full rank because the size of the matrix is 2 by 2 and there are two linearly independent vectors. As for this one, you can see from this that E1 prime, you can see that if this E2 prime you times 3, you get 3 and 6, which happens to be E1 prime. Since there exists a multiple of E2 to get E1, this means that they are dependent. This means that if you were to draw out like the system for this thing, it would be like E1 prime would be here, and E2 prime would be same line, but like maybe further along. This is E2 prime, this is E1 prime. And for this system, no matter how you try and add or you minus E1 and E2 prime, you're still going to be on that same line all the way. You can never go out because there's no vector allowing you to go out. You E1 plus E2, you get a vector along here. You get E2 minus E1, you get a vector still along the same line basically. Since this is a 2 by 2 matrix, it is in 2D space. But we are only able to go along the 1D space of this line. So that means the rank of this matrix is 1. Rank isn't... It's another thing where you just kind of have to know what it is. Not really that useful in any sort of questions. Yeah. Coordinate conversion and mapping, I have kind of gone through this. I can just summarize it again, I guess. Okay, so we have this maps from the... I need to make sure I get these. I always get these two mixed up. Local to global. Yeah. This converts coordinates from local to global. This is coordinate conversion. Now, the other coordinate conversion is going from global to local. And it is the opposite, where your output is the whatever input you have times the inverse. That is for coordinate conversion. Now we do morphing or transformation or whatever you like to call it. This is morphing from local to global. And this is from global to local. This is what we do in our textbook basically. We start with E1, then we change them, we morph those vectors, and then we get our output vectors as a local system. So this uses the same equation in the textbook. It is just AV. And since this is the opposite, this uses the inverse. Just have to take note of which matrix to use when. Personally, I only remember this one and this one, and I remember the other two are opposites, so I'm like, oh, okay, can. But whatever helps you remember. Just know that coordinate conversion and morphing are two separate processes, and you need to know whether you're going from global to local or local to global. Gotta be very careful. And read the question very carefully. Please don't miss out the keywords, whether it's coordinate conversion or morphing. I can't stress that enough. Alright. Gauss-Jordan. It has been 1 hour and 40 minutes, and I'm kind of halfway there. That's not too bad. Okay, Gauss-Jordan. So we have a 3x3 matrix. D, E, F, G, H, I. We have a 3x3 matrix, and we want to use Gauss-Jordan. No, wait, hold on. Okay, hold that thought. Alright, let's say we have a question where it tells us to calculate the intersection point of three planes. You might remember this as a homework question, where you have your first equation, ax plus by plus c, say z, is equal to a number, let's say b1. Can I say b1? Yeah, I can say b1. And then we will have the second, oh, this is plane, not line, my bad. A, B, C, D, E, and F is B2. G, H, I will be B3. So you see we have three equations, basically like simultaneous equations. So instead of writing all these three equations, this can be simplified into the form of Ax equals to B. Yeah, these are vectors. So how you get this form is that A is the coefficients. So A will take this, it'll 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 take this, and it'll take this. X is just X, Y, and Z, your unknowns. And B is just the outputs of the equations. So from here, you can get a matrix equation, which is AX plus B. You have A, B, C, D, E, F, G, H, I times our X, which is our unknowns, X, Y, Z, is equal to our output, B1, B2, B3. Now, to solve this, we could like times the inverse on this side and times the inverse on this side. That would be nice, but this is a 3 by 3, and finding the inverse of 3 by 3 is a pain anyway, so let's not do that. So for yeah, so for this, what we have to do is make something like a augmented matrix. So we're gonna have something like this. We have A, B, C, D, E, F, G, H, I. This is the handout method described in the homework. There's like a Gauss-Jordan handout. That's the method I use. There's the more geometric version as well, which I can go through, but I think this will cut it basically. And then we draw a line, and we do B1, B2, and B3. Now, Gauss-Jordan is all about doing your best to make sure whatever is on this side ends up to be as close to the identity matrix as possible. I didn't mention the identity matrix until now, I just realized. So what that is that you have ones along the diagonal, and everywhere else is 0. And then whatever, like if you, okay, hold on. The objective of this equation is to solve for x, y, and z. That's our unknowns. So we can do this by getting this as close to the inverse matrix as possible. And when we, like swap rows, or like we scale them by like 2 or 3 or whatever, you do the same on this side as well. So after doing Gauss-Jordan, this becomes its own thing. And this here will be like the intersection point of those 3 planes. Now, Gauss-Jordan, I think the handout does a fairly good job at explaining it, so I won't explain too much in detail. You just have to know that you can swap rows. This is like, let's say you swap this row with this row. That's a valid operation. Or you can scale them. That means you can say, oh, this row is equals to the same row times 2. So like, yeah, you apply 2 to the same row, you get 2a, 2b, 2c, 2b1, that kind of thing. And the final thing is that you can take one row and subtract it from another. So you can subtract or add, subtract between rows. The handout does a good job explaining it, so I think you can just look there for the details. Okay, the affine map. The affine map is generally denoted by this. This is the general formula. Oh, that's wrong already. X prime is a point plus a matrix times point minus point. What the heck do these terms mean? Okay, this is your input, this is your output. Fair enough. This is your old origin, and this is your new origin. Affine maps apply to points, so that's why the output type is a point. Okay. Let's look at the slides for this one. There is a pretty good visual example. This is 3 by 3. Ah, there it is. Okay. Here's an example where in this case, our initial origin and our new origin do not change, but I think it's still a very good example. This one says rotate this arrangement by 30 degrees about a certain point. So that means, in this case, we have A, B, and D. Sorry, A, B, C, and D. Can I increase the thickness? We have A, B, C, and D. And it's rotating all about point R. So this is your fixed point that you're rotating about. And because it is fixed, that is your final origin, and that is also your initial origin. And then it says rotate by 30 degrees. So in our case here, this would be the point R plus the rotation matrix when you rotate by 30 degrees, input point minus dr, which is the original. This will be the affine map that you need. Note that this isn't like a matrix where, like, previously it was like, oh, find the matrix, and you go, A is this matrix, and you go, wow, that's the linear map. Affine maps cannot be expressed the same way. Affine maps are an expression or an equation. They can't be crammed to fit into a matrix like this. That can't be done. You have to give it out in full. So, in summary, find the old origin, find the new origin, see what transformation it's going through. So this is the transformation. Yeah, okay. Here's an example where the input point and output point, sorry, input origin and output origin differ. Oh no, okay. Here it's doing a shear, but after it shears, like, this is where you start, and it wants to end up, say, here. If this would be P, our final, and our initial will be R. So what we do is we follow the formula. We have, for any random point, its output will be the final origin plus whatever shear matrix this is. So it has a shear matrix of S and it has the normal of N. So I'm just gonna write this shear. Oh, right. Never mind. Shear of N and S, because the shear is defined by two vectors, the shear and the normal. And inside it we put x minus the initial, which is point r. This is the affine map for this particular one. It's where you shear, and then you shear this way, and you shear this way, and then you move those points that are being sheared in relation to P. P is your new origin. So it'll be like here. If there was a point maybe here, that point will now be here. If there was a point here, it'll now be here. I hope that makes sense. Translations. That's kind of what we're doing, yes. Translations are when your initial origin and your final origin are different. That's how the points like move to a new place. Okay, triangle to triangle mapping. I feel like this part, the textbook does it really well, so I'm just gonna go to the textbook. I had this here the whole time and I barely even used it. Okay, triangle to triangle. Right, so here, this happened in one of the quizzes, I believe. You're given 3 points, and it says, okay, these 3 points became these 3 points. Let's make it bigger. These 3 points became these 3 points as outputs. And they say, okay, find the affine map that did this. So what you do is, you choose any one of these points to be an origin of sorts. So let's get, hold on, this might slow me down. Okay, let's choose A1 to be origin. So with this, we can now create 2 vectors, because point minus point is vector. You can get this one, and you can get this one. Same thing with the other with the output triangle. Yeah, from A1 prime, you get this vector from your origin, and then you get this vector. Now we have 2 input vectors, and we have 2 output vectors. We need to find a map, a transformation, matrix A, whatever, that makes an input vector into an output vector This should look fairly familiar from just earlier. V prime equals to AV. Now, okay, I've done this. Create vectors from those points and say that with the transformation, you get a certain output. And you have 2 equations that do this. So what you can do is you combine them into one matrix equation, just like it says, V2 and V3. So I'm sure I have faith that you guys will know what this means here. It's just, V2, and then you have the X part, the Y part, V3, X part, Y part. And then that is equal to the output version of that. These are currently 2 by 2 matrices. I believe in 3D, oops, I said 3D and I wrote 3, nice. I believe in 3D that you will have to do another set. So it'll be AV4 is equal to V4 prime. We didn't really get tested on this yet, but I feel like we might have to do another set so that we get 3 inputs and 3 outputs, so you can get a 3 by 3 matrix. And because it's in 3D space, 3 by 3 matrix, it just kind of makes sense. Now, Our original quest was to figure out the affine map. And to that, we need to find our A. We don't have to worry about initial and final origin because the question will provide it. It'll give the x and the x prime. Or if it's not there, I believe you can use the Barycentric as the midpoint. Wait, no, can you hold up? Okay, sorry. You will not be given this point. This is an example point. Like, for example, if a point was this, it would be out to this. The only points you are given that make this map are A1, A2, and A3. But we chose A1 as our origin. And our origin, after mapping, became A1 prime. So this is our initial origin, and this is our final origin. That's why in here, we have our final origin, our initial origin, input point, and the matrix. So we have this. We have this. This can be subbed in, so it's fine. We just have to find out what A is. Now going back down here, sorry, it's a bit haphazard. We have made this matrix equation where we have this information and we have this information. So that means we can just get the inverse of it. This is 2 by 2, so you're able to do this fairly simply. This will be v2 prime, v3 prime, and then this will be v2, v3 inverse. And because these are 2 by 2, you can solve with a lot of math, and you will indeed get a 2 by 2 matrix at the end. And once you get that, you sub it all the way into here. Once you have all the pieces, then you can say, alright, this is the desired affine map. So that's how you map from triangles to triangles. I haven't checked the practice final, but maybe it's there, I don't know. It's also got a really comprehensive example, so have a look at it if you like. After that, I believe... Okay. This one, it's a bit weird, but stay with me for this one. Okay. Now, affine maps are a thing, but an affine map doesn't have to be applied only once. You can keep doing the same, applying the same map over and over and over again. So, this is an example of this, where you have an input point is x, then you have a matrix, and then you have a final origin. The initial origin here is 0, by the way. It's just x minus 0. And then they scale the whole thing afterwards. So they're combining different parts. Now, for this is figure 6.7, which should be this one, yeah. They all start at the origin, and then they increase in size as they go on. So this is an example of how these transformations can be like stacked on top of each other, where the origin, the initial origin is the same, still compared to this. So am I saying the right things? Oh my god. 6.6 is which one? Okay, 6.7 is this one, yeah. So you have an initial point which is 0, and you have a final point. Let's say we take let's say each S is its own box, and we take just the point in its corner, which is this one right here. And this point from the origin, the distance is always changing, and the direction is always changing, because the final and initial origins are different. This one's a bit wonky to explain, I apologize, but it's something that came out in homework, and I don't think it'll come out in finals because it's a bit complex, but it's something that that you should know that you're able to do, where you can stack transformations and you can get things out of it. Yeah. Okay, on to the proper 3D stuff. This one is cross product. All right. Okay, the cross product is let's say you have two vectors, v and w. The cross product Alright, should I go into this first? No, I shouldn't. Oh, no, no, no. I'm so scatterbrained tonight, I don't know why.
You're doing great, man.
Thanks. Okay, now we're in 3D space. There's E1, there's E2, and there's E3. I always draw it this way personally. I know some like to put E2 on top, but I don't know. This orientation is fine as long as uh as long as you like. Okay, hold on. Let's get a picture. No, wait, no, I want a picture, not a website. Okay. Your 3D system drawing should be fine as long as you use your right hand. You label one of these axes to be one of the three axes. So let's say your thumb is E1, your pointer is E2, and your middle finger is E3. Then you can draw it as such. You can rotate your hand, but you can't like move your fingers. Fix those fingers, then you rotate to see how it is. Yeah, but personally I always stick with drawing it like this: E1 to the left, E2 to the right, E3 on top. Now with what's on the agenda? Okay, the reason why I always draw it like this is to make sure that it's always a right-handed system. We say right-handed because only a right hand can make this configuration, and it's basically like the default configuration. So I suggest just stick with this. Okay, planes exist. Cool thing. Planes are like a sheet of paper, basically. They can contain points, they can contain lines, they can contain vectors, lots of cool stuff. Planes in 3D will always be given in either point normal form or implicit form. So point normal will be n. You have a vector that is normal to the plane, perpendicular, n dot x minus p is 0. X is a random point on the plane. Sorry, x is a random input point on the plane. Point P is a given point on the plane. These two are given. Or planes can also be written as ax plus by plus cz plus d equals to 0. This is point normal. This is implicit. know that even though you're given an equation in this form, you can still get the normal very easily. The normal for this plane is just A, B, C. You just take the coefficients of the unknowns. Now with the normal, you can do some fairly interesting things, very useful things. And normals comes up in basically the cross product, because a normal of something is, when something is normal of something, it is perpendicular to that something. So if you have E1 and E2, their normal is the E3. And how do we do that? This relates to the cross product. So if we have two vectors V and W in a plane P, let's say on this plane, we have V and we have W. V cross W will create a vector that is perpendicular to both of these vectors. There is the formula, and then there's the geometric formula, then there's the computation formula. So geometrically, wait, hold on. Yeah, geometrically, the length of it will be V W. Oh no. W. Microsoft Paint, come on. Sine theta. But the actual vector V cross W is done by doing the cross product calculation, which is V1, V2, V3 cross with W1, W2, and W3. Now, the way I do it is that I cancel off, I block off row by row, and then I do like a crisscross. What I mean, I'll show you what I mean by this. So we want to find what's in the first row. First row will mean it's, ignore this for now. And then we do almost like determinant, like the motion is the same. This times this minus this times this. So that will be V2W3 minus W2V W2V3. Similar process for the other ones. Now we're doing the second one. We block out the second one. Because second is different for whatever reason, we have to go from here times this minus here times this. So it'll be W1 times V3 minus V1 W3. Same thing for the last one. Cancel out that row. This will be V1 W2 and W1 V2. This gets you the actual vector produced when you get the cross product. This only gets you the length. So know when you have to use which one. Now the cross product is picky. This V cross W is not the same as W cross V. The order matters here. In fact, if this V cross W, you'll get a vector pointing straight from the screen into your eyes. This one will go the exact opposite direction from your eyes towards the screen. So it's very important to make sure you get the direction right. And how do you get the direction? You use something called the right hand grip rule. This is right hand grip rule. So you can see that there are fingers and they are curved, and then there's your thumb. Your fingers are like your input, your thumb is like your output. Starting from here, if you want to calculate V cross W, we put our hand on V and we curl our fingers to get to W. And after we finish curling, the direction our thumb is pointing, in this case straight up, is the direction of the normal vector. Sorry, it's the direction of the result of the cross product. Now, you could also say, oh, couldn't I curl my fingers like this way? I mean, you're technically right, but to make this work, you have to go the shortest curling distance. So let's say we try W cross V instead. If we try W cross V, we start at W, we put our hand at W, and we use our right hand to curl to get to V. And to get the shortest curling distance, we would have to put our hand upside down in order to curl the shortest distance, in order to curl this way. Once we finish curling, we find out that our thumb points straight down. Oh, sorry, it points straight into the screen, yes, which is in the opposite direction from what we got here. So be careful about the signs that you use. Yep. Okay, scalar triple product. I love saying it because it sounds really cool. I don't know, it's probably just me. Okay, the scalar triple product is a really useful thing to calculate volume in a 3D space. Okay, volume will be... Okay, I should use the slides for this. Sorry for all the flashbang. I don't know why my computer does this when it goes from slide to slide. Okay. Right. Now, the scalar triple product is a way to calculate volume, like I said. Let's use white. Right. And how you do this is that you want to get the area times the height. Base area times height. That's straight from primary school. I forgot to mention. Okay. The cross product. I mentioned that the value of the cross product is VW sine theta. The value of this cross product is this, but it is also the area of the parallelogram formed by those two vectors. In this case, if we have V and we have W, we can get this area. The number we get from doing this calculation will be the area. So in this case, V cross W, we have V and we have W. So in this case, it would be this area, because V and W, you get the parallelogram formed by those two vectors. Now the scalar triple product calculates volume. I've said that like 3 times, but let's actually get to it. We want the base area. So, knowing that the cross product gives us an area, we just have to cross 2 vectors and we get the area, which is as such. In this case, u cross v. So we get u cross v. This is our base area. Now we want to times by the height. But you can see that the direction of the W may not necessarily be fully vertical, so we have to improvise. This little triangle here, let me just redraw it. This will be like this. This will be W. And then there's like a theta. And this height is the height we actually want to get. So doing some trigonometry, we can find that that height is W cosine theta. Sorry, magnitude of W cosine theta. And since this okay, since this is the height, we can say that our volume will be dW times, oh no, hold on. W cosine theta times height. Base area times height. Now this gives a number, and this gives a number as well. But you can rearrange this to get W U cross V cosine theta. And this looks very similar to our dot product formula. So this is how we get the proper formula for the triple scalar product. W dot U cross V. I'm pretty sure I didn't mess this up, but I'm going to check nonetheless. Yep. Luckily the order here doesn't matter, because you're ending up getting a volume anyway, which is going to be a positive thing. So you just choose any 2 vectors to cross, and then dot that with the third vector. Then you can get your volume. That's done. 3D interactions, lines and planes. Okay. I think I'm gonna take a water break for a bit, so I will be right back. I love the chat, guys. Keep it up. I've only just seen it, but I love it. It's beautiful. Oh, I thought U cross V gives the normal perpendicular to the height. Give me a second. Okay, I thought U cross V gives you the normal, which is the perpendicular height. Okay, I see what you mean, Kami Taka. I hope I said that right in the right way. This, I get what you mean, but this is not a given. They could say that the volume is bounded by a certain three vectors, u, v, and w. But here, it says that you're only using u and v in your working, and w isn't mentioned at all. So you will get a volume, and it will be like an actual number, but it will not be the number that they want because you're not using w. You have to use all three vectors in order to get your volume. It is true that u cross v gives you a perpendicular vector, like a normal that goes straight up, and you could think that, oh, you just use that length. That depends. If that's exactly what the question wants, sure. But chances are that's not going to be the case. So please use all three vectors and use the scalar triple product formula. Holy shit, I've been going for 2.5 hours. God damn, son. That is tempting. What do I have left? I have these things left. Honestly, not too bad. I mean, I've already mentioned this. I've already mentioned this. I've kind of already mentioned this. I definitely have already mentioned this, so it's mainly these. Yeah, I think I can do it. I think I might be able to do it even before like 1 a.m. Also, I am so sorry this is taking this long. Salute to all of you guys who are still here after like I started 2.5 hours ago. Hormat, thanks for all y'all being here.
Thanks for your help.
Yay!
Yeah, we're gonna get cursed if it hits 1 a.m.
Seems good. Alright, my throat has had water. Let's see what we can do next. Done. Interactions of line planes, plane planes, point plane, line. Alright. Line and plane. There is plane, plane P, and there is a line possibly going through it, possibly not. There is a line given as P plus TV, and the plane will be given as There should be a colon, not an equal sign. I'm a stickler for these things. This will be n dot x minus q. A point on the plane is 0. We have a q point here. Now, you might be asked to calculate the intersection of these two things. We know that the line is p plus tv. So any point on the line is p plus tv. So this is valid for any general point. It's just that the value of t will change to whatever. And we know that this is the equation of a plane, where this is our input point. And since that's our input point, and we have a point, so we have an expression that represents any point on this line, really. If this is substituted here, and it equals to 0, that means this point, this point is on the plane. So we sub it in. It'll be n dot p plus tv minus q equals to 0. Then you get n p minus q plus tv. I remember that all these things here, these are all given except for t. This is known, this is known, this is known, this is known. The only thing that's not known is t itself. So by rearranging this, you can get t as, let's see if I can get this right. This should be p minus q dot n over v dot n. Now take note that we are dividing by something, and that's generally a scary thing, because what if it's 0? With this, if v dot n is 0, that means that these vectors are perpendicular. If n was going straight up like this, and imagine if our v was perpendicular, it would be like this. And it's a bit hard to see in this 3D space because my drawing kind of sucks. But if this were to be the case, you would end up with a line that is like parallel to the plane. It won't intersect. It will be just nice parallel. And because this is 0, there will be no possible t where you can ever intersect because it's parallel. It's floating above. And in that case, there is no solution. But in the case that it's not parallel, it will be like this, where you have a t, you find that t, and once you find it, you sub it back inside here, and you get your intersection point. Okay, that's line and plane. I don't think there's anything else with line and plane. Distance from point to plane. 3 planes. Okay, intersections of planes. This one is Gauss-Jordan. You know how I had the matrix earlier, where it was, I had like the augmented matrix. I had the 3x3, then x, y, z equals to b1, b2, b3. All these are you can get from these words. Depending on the equations of the planes you are given, you may have to convert to implicit or whatever. But if you do convert to implicit, you can do this form, where you can make it into a matrix equation, and you solve via Gauss-Jordan elimination to get your x, y, z. Yeah. Now, in the homework, I'm sure you guys remember, there was, or you may not always remember, but there was a case where you had two planes, and this didn't exist. It was like 0, 0, 0, and you had maybe A, B, C, D, E, F. Now, what happens if this is the case? Did I scan my homework? I can just show my homework if it's here. Homework 7 maybe? Oh my god, the lag. Ah! No, not 7. 6? J1, J2, J3. Ah, perfect. Alright. So, here we were given two planes. But it's like, okay, find the intersection. But if you hold out like two pieces of paper, they can either be parallel or they will intersect in a line. There's only two options for two planes in 3D space. Oh, sorry, there's a third option where the two planes are exactly the same and they intersect at all the points in the plane. But as you can see from here, if you maybe like you times 2 this, you can see that this is not equal. So they're not the same plane. So that's one possibility down. You can solve this via Gauss-Jordan. The way I do it is with the augmented matrix. And you do the row operations. Like I said, you swap. You can swap rows. You can scale rows. And you can swap scale. And you can plus and minus different rows together. Oh, writing on lined paper is actually damn nice. Yeah, so you can do your Gauss-Jordan process and you eventually hit a choking point. It's a bit small, so I'm going to rewrite it here again. I hit 1, 0, 0, 0, 1, 0, 1 third, 1 third, 0, minus 1, 1, 0. Now in regular Gauss-Jordan, you'll be like, hey, there's supposed to be like a 1 here. That's not here now. What do I do? Well, you take a step back and go, okay, let's just convert this back into normal equation form. That's what I've done here. Now you see that x, there's an equation for x and an equation for y, but z is its, how do I put it? The top equation is usually for x, the bottom is for y, and the bottom is for z. X and y have their own equations, but z does not. By this, you can see that you can call it that z is a free variable. That's what it's like formally called, but basically it's like a parameter that you can change. So since there's nothing defining what z is, we literally don't have an equation for z. We have no clue. It could be 1, it could be 2, it could be 6, it could be 69. We do not know. So we let it be a parameter. Let z be some number, let's say t. And then we sub this back into those equations. And what we end up with is that you end up having a number plus t and another number. This is, you can combine these things into one line equation where you can see that you have this expression for x now, you have this for y, and z is just z equals t, which is z equals 0 plus t times 1. And with this, you can look at the coefficients and coordinates, and you can fill them in into the line equation. Stop me if this is getting too complex, or if I'm saying terminology that's not making sense. But yeah. So we start with the point, with just the number sitting by itself. We have -1, then we have 1, then we have 0. -1, 1, 0. That's the point. We have t, we have t, we have t. That's the scalar. There's our t. Then we have the vector part, which is what is being multiplied with t. -1/3, -1/3, and 1. -1/3, -1/3, and 1. This is how you get your p plus tv. In this case, the planes weren't parallel, so they had to intersect at a line. And this is that line. Yeah. That is the intersection, that's the interaction between two planes. With 3 planes, there's quite a few interactions that can happen. Let's just look at the picture real quick, because it can get wild. 3D plane images. Not quite what I'm looking for. What the heck is this? 3D plane Gauss-Jordan, maybe? Solutions. What? '3D plane. I don't want airplanes.
Maybe you got like math or something.
Yeah, that's a good point. Hold on. Math, baby? Yeah, let's go. Absolute legend. Okay. Okay, this is one scenario where all 3 planes converge at a point. The yellow plane, the green plane, and a red plane. All at one point. If only things were always like that, but unfortunately they are not. Can I get one with all of the scenarios? There's 2 planes. I know there's the picture with a lot of different things. What the hell did I search to get that? Yeah, okay, this is one of the different scenarios. There are 3 different planes, brown, blue, and green. But you see that they don't intersect at a point, they intersect at a line. So with this, when you Gauss Jordan, you'll run into something weird again. But you don't have to fear, you just have to follow the steps that I mentioned just now. If you run into weirdness, set it back to an equation, x equals whatever, y equals whatever. See what variable is not defined by a proper equation of its own. Make it its own variable, like z equals to t. Set that back in, and then make a line equation from that. Now,
Wait, sorry, just
yeah.
for the z that is always 0, do you always put it as t? Is it always t?
For like just now the question I went through, is it? Is that?
Okay, the z for the z.
For the z, you set it to a variable t because you don't know what it could be. So if you had that, it would be x equals to something, y equals to something, z equals to t, which is 0 plus t1. We don't know what the value of t is, so we just have to make a how do I say this?
Just set it to something.
Yeah, you have to set it to something so that all 3 can be defined by one t variable.
Okay.
Yeah, that's how you get the whole p plus tv. So that t is the one thing that's changing that gives you that whole line. Yeah. Okay. Now that's done. I think I just did that. Distance between point and plane, this is fairly manageable. Alright. Point and plane. Whoa, that's a big plane. We have plane P, and with the plane we always have a normal, and we have some point on the plane Q. Because the plane is defined by n x minus q is equals to 0. And then we have a random point r sitting on top, and we want to find the distance from the point to the plane. We want to find this distance. Now, what you can do is, for this type of question, get the vector from q to r, or r to q, doesn't matter. You want to create a vector from these two, so you get q minus r in this case. And then, some of you might be able to see it already, you project that onto n. And the length of that projection will be the desired length that you want. So, that will be length of projection of onto n q minus p. That is q minus p dot n. We're doing the length, so it should just be this. Does it make sense? I hope it does. I can also draw this triangle like this, where we have q, we have r, and then we have n, which is like here, I guess. So we're projecting this vector onto n to get this length. Yep. And distance between, yep. Oh, I thought that was a question. Okay. Distance between lines, alright. This one involves skew lines, which is a new thing in 3D. Because in 2D, lines either intersect or they don't. But in 3D, they can dodge around each other, and that's kind of annoying. But whatever, we take those. Distance between lines. So first of all, we need to consider if they even intersect at all. Because if they intersect, that's going to be 0 anyway. So you can... hold up. If it's parallel... There's like a certain flow you want to... There's certain things you want to check first before others, but I don't recall that right now. I know one of them is checking whether the two... let me just write down the line equations. L1 is a point, TV1, and then we have L2 being P2 plus SB2. Now, if V1 is parallel to V2, you can say that there's like definitely a distance there. And if... hold up. If it's parallel, that means... Wait, hold up. Parallel. My brain GPU has slowed down. God damn it. P1, P2. Find this vector. they're parallel, I can't cross product. Huh? Homework time. I know it's a homework question. Not this one, I think. Yeah, not that one. Okay. We have two lines. Then I say if they are linearly independent, so that means they will that means they are vectors of their own, they're independent, so they can be like this, for example. My U and V look the same all the time. That's why I use W, because I don't trust myself. Well, now I know what part to revise for because I couldn't remember this off the top of my head. Find generic point, find generic point. Okay, okay. So if I have a line, like say like this, then it will be generic point, that will be here. This will be P, this will be Q. X2 and X1 will sit on top of each other if I remember correctly. U cross V, you can only do that if oh, you just find N. Oh, LMAO. Okay. Apologies, back to this. If they are parallel, you can use one of the vectors, say V1, and find a vector that is perpendicular to it. So that will be, say, V2, V1. There's a way to do this in 3D, the equivalent, but I forget. Oh, I know Samson went through it. Did I record it? Shearing Gauss. It's not this one, right? No, it's not this one. Alright. Never mind. Okay. Basically, you find a vector that's perpendicular to it. And that will be something like this vector. And then in that case, if these two lines are parallel, you can get this vector, P2 minus P1, because, you know, they're given. And you project that onto this newfound perpendicular vector. And then you can find the length of that projection, which will be the distance between the lines. So that's if they're parallel. If they are not parallel and they do not intersect, that's when you do skew magic, basically. Okay, this U cross V. If it's parallel, okay. Alright. Now, this is in the case that they are parallel. But now let's do the case where they're not parallel. If they are not parallel, so V1, in that case, we want to get an example point, some sample point on L1 and some sample point on L2. So let's call this X1. X1 will just be P1 plus some T V1. And same with X2 will be P2 plus some point, some S V2. Now, for these skew lines, they will be. Can I GeoGebra this? I think I might be able to do that. Oh, that's wrong. Nice. I'll give it one more try. If not, then I'll attempt to draw it. Whoa. Oh, I'll attempt to draw it then. Basically, you have the two lines that are on top of each other, but they do not intersect. So, no, cancel the... leave. So you have one line that is below, so to speak, and then another line that's on top. So it'd be like that, like that. So in this case, black is on top, I guess you could say. Now, x1 and x2 are our general points, and we want our general points to be sitting right here. So x2, let's say x2 is the one that's black, so let's put this is line 2. No, line 2. The one in red is line 1. Then x2 will be on the black line, and x1 will be on the red line. Now, the vectors, this will be v1, and this will be v2. Now, for the properties of the cross product, if you take the cross product of v2 and v1, this should be parallel to x2 minus x1. This one needs a second, so think about it for a bit while I go have more water. It's like, try to visualize the output of the cross product and where the points are in space. I wish I could use my camera, but I actually don't have it with me right now. Yeah, so with that cross product definition, v2 cross v1 should be parallel to the vector of x2 minus x1. And if they're parallel, if we apply the the dot product formula, we can write the following. And the angle between this vector and this vector is 0 because, they're parallel. And then, because they are 0, this part becomes basically times 1, so that disappears. Then you can rearrange to find this. This is the actual distance that we want to find. Because remember, x2 is on one line, and x2 and x1 is on the other line. So finding the distance between these 2 points will end up being the distance that we want to find. The shortest distance between those 2 skew lines. This answer isn't simplified, but the TA marked me correct, so I don't know what they're doing. This needs to be simplified further because we found x1 and x2 to be the following. We found like general points, so by right we should sub those in and simplify. Yeah, that's it for skew lines. This is what I mentioned earlier before I cleared this. This is if they're parallel. And this scenario is for this. And of course, if they intersect, the distance is 0. I believe that's it. I have mentioned 3x3 determinants. There is no change for linear map and 3D map. Linear will still be v prime equals to AV, and f prime will still be x prime equals to final origin plus a input point minus initial origin. These will still hold in the third dimension. Rotation matrix. Okay, I did mention the R1, RE1, RE2, RE3. General rotation. Ooh, I would suggest just reading the handout. But if you guys are still confused about the general rotation one, you guys just PM me. Because it's 1 in the morning, so let's try and wrap this up now. Combination of maps. It is, yeah, you stack maps upon each other. I have gone through this before, like when you want to apply like a shear and a rotation and then, sorry, scale rotation, then like a shear, the order matters. Even in 3D, you still got to be careful which way you write it. Whoa, that's a lot of people. And then the 3x3 inverse, I mentioned you should use Gauss-Jordan because calculating it by hand is a bitch. And with that, bonus doesn't exist. Good morning, everyone. Oh, wait, I didn't split the timer. Time. All right, let's go. All right, I'm not sure how effective this was considering how tired I got by the end and I started messing up.
Hey, thanks for the
stuff.
treat, man.
Yeah, no problem. If you guys are still confused, I'm sure I'll be more awake and alert tomorrow, so I can answer better then.
Appreciate you.
Yeah.
This is being recorded, right?
It's
Monday
okay.
lesson.
Fuck, I made you guys stay for another Jan lecture without Jan. I'm so sorry. Oh,
This stream is being recorded, right?
it's on Twitch, yeah.
Okay, great. I can just go there and find it again because I'm pretty sure my half asleep brain could not register the tail end of this.
Yeah, dude, my brain couldn't half register the tail end. This part, my brain just faltered at the end. I was like, huh? I need to check my homework.
To think of it, you have finished just shy of a full Monday lecture anyway.
Pretty much, yeah. All in like every topic. Oh my god.
Alright, guys, lunchtime.
Alright, lunchtime. Let's go.
Thank you for the mass. It's time to say goodbye, everybody.
Yo, where's that coming from? Holy shit, that was cool. Do it again, do it again, do it again, do it again. Do it again. Ah, okay.
Thank you, Mr. Luigi, for the mass.
Yo, let's go! Thank you. All the best to you too. How do you do that? Like voice synthesizer? 4 minutes until curse. Nah, man. Nah. Curse never happened. No curse, no worry.
Gotta rewatch the whole entire thing again.
You put it as background noise when you do other things today.
Because I fell asleep.
Okay. Let's look at Twitch chat. What does Twitch chat say? Wow. I talked about this. God damn, son.
Prof. Luigi MVP.
It's been a journey. I need to follow all you guys after this. I should do that. Look at that. Educational English speedrun. Wow.
In the case of Basic Linea, you cover the entire syllabus in one math lecture.
I mean, I covered it in not like ultra depth, but it was done. It was in fact done. My computer has been lagging too. Like I don't know if it was apparent, but when I draw on paint, sometimes instead of a curve, like I write the letter C, it just becomes like a line. It's like what? Yeah, that's weird. Alright. Well, thank you all for coming, and I hope you gained some stuff out of this.
Well, have a nice night. Is it even night anymore?
Have a nice morning.
Have a nice morning. Good morning.
See you tomorrow.
Literally,
Literally tomorrow.
we did an exam, so yeah, that's successful.
13 weeks summarize the 3 hours stall. Compression. Hell yeah. I love compression.
Wait, this is a dumb theory, but if John went at your speed, would he have finished the lesson in week 1?
No, I think the reason why he goes as slow as he did is because he has to set up context for everything. What I did here is that I already had context for you guys. I'm sure you knew how to do points. I knew what were vectors. I know you know what were matrices and all that. Granted, I still went through for those who still somehow may not know, but it takes time to set up that foundation, which is why it takes pretty long.
I guess today cleared up my, because I was really rubber about lines. I don't know why.
Lines,
I think
okay.
Yeah, but I think the 2D lines I'm set.
2D lines should be alright. 3D lines, there is a section in the textbook that basically describes how to solve for skew lines. You just have a look at that.
I realized I was overthinking about 2D lines.
God damn it.
Yes. That's why I'm going You see me draw option G, here it is.
Oh, I should end the stream. Alright. Good night.
Good night, everybody.
And
Guess I'm so you can study for math tomorrow.
yeah. I still have to do the midterm, the final practice somehow.
Amen. Oh, but Tesla's easier to watch, no joke.
The stream is at where? I think like the recorded stream is at where?
Yeah, you check my Twitch.
Oh, okay. Thanks.
Yeah. I had to read all the messages I missed. Just look at his Twitch VODs. Do I get raid benefits? Maybe. I don't even know what a raid benefit is. Oh wait, no, new people came. I didn't do the thing. STU, and then I do a little wave, and then I do a little, where is it? Another wave. The person's name is Pineapple, I approve. Oh. In future for math. Oh, we'll see. Oh no, Discord lag. Hell no. Okay. Yo, let me read you. Idea? You can do it. Pineapple. Skip to. Oh, right. I did. Demo recording. That was me. Saved on Twitch. That's me. It is indeed saved. Corner conversion matrices. I did do that. Okay, that's good. Yep. Speedrunning that time. Yeah, I put the timer there because it's like, hey, if I say it's gonna be a speedrun, it'll be a speedrun. Damn it. I mean, I had the timer in my computer anyway, so I might as well. Yeah, imagine timing each chapter. Ooh. Oh, I should make splits next time. Oh, that'd be cool. Why am I invisible? Huh? Oh wait, is it cause it's a... Hold up. Whoa, whoa, lag, no. Oh no. Amazing. The whole vid is 8 gigs? Oh my god. Holy cow. Oh, I think it's cause I'm streaming that this thing is purple. Yep. Yep. No difference. I think that's it. Yeah. Reset. And exit. I guess it is worth it in the end, yeah. Kill stream.